All right, let's do some L'Hopital. So with this first problem, we're going to, first of all, note that, always we want to make sure that we have a L'Hopital's rule indeterminate form. And in this case, cosecant of x, cosecant of 0 is undefined because cosecant is 1 over sine, and then 1 over 0 so you have, this is sort of an infinity minus infinity situation, which really isn't an indeterminate form, but we can turn it into an indeterminate form by doing a little bit of algebra. So the first thing I'm going to do is do the aforementioned conversion to 1 over sine. And then I'm going to write this as a single fraction by finding a common denominator. And the common denominator here is sine of x times x. And so I'm going to have to multiply that times x. And this one is going to get multiplied by sine of x times x. And then you can combine these as a single fraction. And this does have the L'Hopital's rule indeterminate form. You would want to actually double check this, but I'll just talk through this, that the limit as x approaches 0 of the top is 0 minus 0, which is 0, and then on the bottom you get 0 times 0. So each of those do have limits of 0. So this is L'Hopital. And so you can go ahead and do the derivatives. 1 minus cosine. On the bottom, we're going to have to use the product rule. So that'll be sine of x times the derivative of x plus cosine of x times x. So in this case, I believe I get another L'Hopital's rule indeterminate form. So this is L'Hopital again. And of course, you'd want to write down, if this was on the test, you'd want to actually write down the limit as x approaches 0 of 1 minus cosine of x does equal 0, and the limit as x approaches 0 of sine of x plus cosine x times x does also equal 0. So that's what makes this a L'Hopital's rule indeterminate form. Make sure you write that down if this was a test problem. I was being a little lazy earlier. Okay, so let's apply L'Hopital's rule a second time. Here we end up with, let's see, sine of x on top. On the bottom, this will be cosine of x. Okay, cosine of x plus sine. So I had to use the product rule there. I think I got all that correct. And now I can actually plug in my 0. And I get 0 over 2. So this one is 0. All right, let's take a look at this next one, which is still its tangent of x to the x power. And so this is definitely not a L'Hopital's rule indeterminate form. So we're going to have to do something about that. So indeed, what do we do? All right, so this is going to be a big pain because we're gonna have to do several conversions here. So what I'm going to do is I'll do this in stages. So I'm going to let y equal the tangent of x to the x, and then I'm going to compute the arctan of y, which is just going to be x to the x. So that's my first little nugget that I'm going to do. And then just to keep things, well, I guess we can just keep going with this, can't we? Sure. And then I'm going to do the natural log of this. And so the natural log of the arctan of y is equal to the natural log of x to the x, which I can rewrite as x times the natural log of x. So now I'm doing the limit as x approaches 0. And so this would be 0 times negative infinity, really, because it's the limit as x approaches 0 from the bottom. So let's do this limit. So if we do the limit as x approaches 0 of this, we'll be able to plug that in to work our way back to figure out what the original limit was. Okay, so to do this, I need to rewrite this. Anytime you have 0 So this is 0 times infinity. Anytime you have something like this, you want to reciprocate something. In this case, I'm going to do this. Natural log of x divided by 1 over x. Let's get rid of that because it's not really correct. And so that's what I'm going to do the limit. So I'll do the limit as x approaches 0 from the top of the natural log of x over 1 over x. So let's do our derivatives. Oh, so this does give me this. Limit as x approaches 0 from the top of natural log of x is negative infinity. Limit as x approaches 0 from the top of 1 over x is equal to infinity. And so this is an infinity over infinity L'Hopital's rule. So we go ahead, and then the derivative of that is going to be negative 1 over x squared. Now, before we do anything more, so this is here, I should have written this down. L'Hopital. Okay, so at this point, we're going to do a little bit of canceling before going forward. We get 0, or I'm sorry, negative x. Yeah, sorry, I was getting a little ahead of myself. So you flip the bottom one, multiply. This is what we get. So this is going to be 0. Now I have to work my way back. So let's see, what did we just do? We just found out that this was 0. So the natural log of the arctan of y is equal to 0. I got to figure out what y is. Technically, I should have made y equal to the original instead of that. But anyway, so now let's work our way back. So that means that the arctan of y is equal to e to the 0, which is 1. And then y is equal to the tangent of 1, which I don't know what that is. I'm just going to leave it as this. So there's my answer. All right, let's try these others. We got a multiplication problem here. As you know, this can be 0 times, something undefined. Wait a minute. 1 over, yeah, this thing is, this thing just doesn't exist. Okay, so this doesn't exist. You really can't use L'Hopital's rule here. So you may be tempted to try to use L'Hopital here, but the problem is that this isn't 0 times infinity. Here's the problem, is that the limit as x approaches 0 of x is 0, of course. The limit as x approaches 0 of sine of x, 1 over x, does not exist. It does not exist. It simply does not exist. That is to say, it's not infinity. It just doesn't exist. And so this doesn't exist. So I took this out of our textbook, so something snuck through, I guess. It wasn't L'Hopital. Let's try this last one. This one is 1 to the, so if I were to, 1 to infinity, right? Because 1 plus 1 over infinity, that's 1. And then you've got that x becomes infinity. So this thing, it's not an infinity over infinity, but we can manipulate this. And the way we're going to do this is we're going to do the same thing we did with the previous problem and do the natural log. Limit as x approaches infinity, natural log 1 plus 1 over x to the x. That means that's the limit as x approaches infinity of x times the natural log. Okay, well, it's still not L'Hopital. I could write this as 1 over, there, that'll do it. Limit as x approaches infinity of the natural log over 1 over x. Now this is L'Hopital. And the reason is that the limit as x approaches infinity of the natural log, that equals 0. and the limit as x approaches infinity of 1 over x equals 0. So that means L'Hopital. So let's do it. Do our derivatives. Okay, so the bottom one's easy. The top one, I'm going to have to use the chain rule. I think I did that right. And now I can see that these will cancel. And I'll be left with the limit as x approaches infinity, which is 1. And now I can work my way back. The natural log of y equals 1. So that means that y is equal to e to the first, which is just e. 2.71828. So that's it. Don't forget to smash that like button.